Today, we want to talk about complex numbers because no math is complete without at least a little bit of weirdness. So let's get everybody up to speed on this complex number business. And we can see where trig enters into it. So think back to when you first started learning about square roots of numbers. We know that the square root of a number is when we multiply a number by itself. That's how we make a square. Square root is just undoing that. Now, back in the day, you learned about the square root symbol, and you were trained to say that the square root of -4 is not a real number. We didn't say that there wasn't an answer or this was undefined. We specifically said this is not a real number, which sounds a little bit like an insult, but we were specifically trained with this phrase, not a real number. And of all the weird math phrases that say things like no answer or undefined or does not exist, we were specifically taught to say this phrase, not a real number, which raises the question, what kind of number is it? I don't recall learning the phrase not a real number and having anybody in the room ask, well, then what kind of number is it? But then again, I remember that this was taught to a room full of teenagers, and they were too cool to care about things like this. But this raises the question, so what kind of number is it? So we did not like this situation when we're like, oh, the square root of -4, we can't take a number and square it and come up with a negative, because a negative times a negative gives us a positive, and a positive times a positive gives us a positive. When we square something, the signs are always the same. If we find the square of something, it's that thing times itself. Because if we're multiplying something by itself, then the signs have to be the same. But we can't have this thing be positive and negative. So we did not like this situation where we square something and only come out with a positive number. So we made something, like I was there. I missed that meeting. So we invented the imaginary unit. Is imaginary airy or airy? Imaginary. Airy. Thank you, Siri. I like how I just said the word imaginary and Siri knew I was talking about math. Siri's like, oh, yes, of course. I know you are a nerd. So just go immediately to that. Or she knows I was talking about imaginary numbers and she's been listening this whole time. It's a little bit creepy, Siri. Stop spying. So we invent this number called the imaginary unit. And this is what we do. We said I is a number that when we square it, we get -1. I squared is -1. We could also think of it as I is the square root of -1. This allowed us to write something that wasn't a real number for the square root of a negative, but was an imaginary number. So to use this, if we want the square root of -4, we just think of this as the square root of 4 times the square root of -1. So that's 2i. Two I is an imaginary number. This is how we'll deal with the square root of a negative number. Now, if our square root is not a square, so if I've got something like the square root of -5, we can simplify the square root of -1 parts. -1. So if we're going to be left with a square root, we're going to be left with a radical as part of our number. We write the I in front of the radical. So when we're simplifying our radicals, if it's a -4, we can take the square root of 4, it's 2. That goes in front like a normal coefficient. But if our coefficient has a radical in it, like the square root of 5 is going to stay the square root of 5, we put that at the end. We put the I out in front. If we're going to square lots of things, or if we're going to find the square root of multiple things, like if we had to simplify the square root of -20, any whole number parts we'll write in front of the I. Any radical parts we write after the I. So the 20 breaks down to a -1, a 4, and a 5. The square root of -1 is I. We knew that was going to show up because of the square root of a negative number. The square root of 4 is 2. That's like a whole number without a radical part, so that goes out in front. And the square root of 5 doesn't get simplified, so it goes at the end. The main reason is we don't want it to look like the I is sitting under the radical, so we write it out in front and avoid that mess. So write the I after any whole number, but before the radical. I think I said that backwards. Write I after the whole number parts, but before the radical. So I goes in the middle. 2i, I times the square root of 5, 2i times the square root of 5. That's the order that we're going to write things. It's not wrong to write square root of 5 times I, but it's not very clear, and so we could improve. It's kind of like an Oxford comma. There's no reason to not use an Oxford comma. Just use the Oxford comma. It increases clarity. So now we've got these two kinds of numbers. We've got imaginary numbers and we've got real numbers. If we combine the two, that's where we get complex numbers. So a complex number has this form, a plus bi, where a and b are real numbers. The reason that we want to stipulate that a and b are real numbers is that if b is a complex number, that it means it has I as a factor, then it's got an I times an I, which is an I squared, which is a -1, and all of a sudden it's real. So we want to have a real part and an imaginary part. A is the real part of the number. And B is the imaginary part. And here's where we have what we have is a complex number. So when we first start learning about numbers and start classifying numbers, we learn about whole numbers, we learn about integers, we learn about rational numbers, we learn about real numbers. Now we're just taking all those real numbers that we know about and putting them inside the set called complex numbers, which have imaginary numbers and real numbers. So we should note that all real numbers are also complex numbers. So all real numbers are also complex numbers. They have 0 imaginary parts. The real number 5 has 5 for a real part and 0 for an imaginary part. So the real numbers are a subset of the complex numbers. Real numbers are a subset of the complex numbers. Usually when we first start talking about radicals like square roots, we say the square root of a negative is not a real number and we leave it at that. The first appearance of complex numbers is traditionally when we're solving quadratic equations. Our usual first appearance of complex numbers is solving quadratic equations. If we think back to solving quadratic equations, we're taking the equation ax squared plus bx plus c equals 0 and writing as a solution x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This happens to be a trash formula, but it's the one that most people remember, so that's why I'm using it now. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's not even how you could say that. That's the traditional words that go along with this formula, but that's not really a good way to read that. It's a pretty handy way to remember it, but if someone doesn't already know the quadratic formula, that's not going to communicate it to them properly, unless they have the same set of cultural assumptions that you do. But that's all beside the point. The other way a quadratic function can show up is in vertex form, which is far superior. In which case we have x equals the negative b over 2a parts plus or minus the square roots. Oh, I should write the one in the middle with the h and the k. In the vertex form, the x only appears one time, so we can solve this equation by performing inverse operations in reverse order. So x can be, let's see, we'll subtract k, divide by a, then take the square roots, and then add h. So h plus or minus the square root of negative k over a. So here we could solve by doing inverse operations in reverse order. The important thing to note here is that these solutions have this square roots, and that square roots could produce negative numbers, and those negative numbers will produce complex solutions. So these square roots in our formula could lead to complex solutions. So since there are radicals in the formula, that puts complex solutions in play. So if we have x plus 3, or the square of the sum of x and 3 plus 16 equals 0. It's in vertex form because I didn't want to bother completing the square, and I definitely didn't want to use the quadratic formula. But the first thing that we do is we subtract 16, and then we try to take the square root of both sides, and that's where the radicals show up. So in solving, the first thing that we would do is say x plus 3 squared is equal to negative 16. So x plus 3 is plus or minus the square root of negative 16. And so here's where the complex numbers have showed up. We would simplify the square root of negative 16. 16, the square root of 16 is 4. The square root of negative 1 is I. So I'll write the whole number 4 and then the I. So negative 3 plus or minus 4i. Any questions? So here we were able to perform inverse operations in reverse order because the x only appears one time. But if we had some other quadratic equation, like x squared plus 6x plus 25 equals 0, then we could use the quadratic formula. Or you can look at my example here and say, are you cheating? And I might go, yeah, totally. 25 minus 9 is 16. So really, this is the same equation. I actually didn't want to complete, I didn't want to use a quadratic formula. We just uncompleted the square. But if we do b squared minus 4ac, that will come out to a negative number. 36 minus 100 is a negative 64. So we're still going to have the complex solutions. The square root of negative 64 is going to be 8i, but then it's going to be divided by the all over 2a. So that's going to give us the 4i. So we did the same thing. Any questions? How's everybody okay? Because at this point, you're all looking at these complex numbers, and it's like, oh, dude, there are no real solutions. Why do we care about equations that don't have real solutions? The problem is, the time you learn about complex numbers is a little bit early. It happens way too soon, way too long before complex numbers kind of become relevant in your applications. At which point, all of your math problems become kind of contrived. So if I start doing applications of this, they're all just kind of contrived problems to make you do the thing, to make you feel better about doing the thing, instead of just me saying, do this thing 1,000 times. So instead of just saying, solve these bunch of quadratic equations because it's good practice and it'll make you better at solving equations, students be like, why am I going to do this? It's like, oh, well, let's suppose that a farmer is building a fence on the side of his barn, and he's got a certain amount of fence, and he's only got to enclose 3 sides. It's like, well, why doesn't he move it away from the barn and make a square? Better yet, if he wants to maximize the amount of area inside, why not make a circle, right? But anyway, we end up with making up these problems. My favorite version of that problem is that someone's going to build fence on 3 sides, and on the other side is a river. I'm like, are you kidding me? This is a class that's supposed to lead to like engineering. You're not going to have like a river there. And so I'm going to put 3 sides of this fence up against the river. Are you going to put stuff inside the fence? Because it's just going to drown when it rains. I know it's, some of you all might be from California. So rain is when like water comes falling down from the sky. Everything gets wet. And sometimes if it doesn't drain properly, then it just kind of fills up. Like when your tub clogs with all the hair and stuff like that, and then it doesn't drain properly, and so it starts to fill up. That can happen like on the ground when the water falls out of the sky. That's called rain. I know we don't have that a lot here in California. That is a lazy ass joke to be in California. Because like what happens when it rains? The lazy joke is California's like, oh, this is good. We need this. People are going to die because we don't know how to drive when this happens. Because it's been a long time since it's rained. We've dropped all this oil on the road. And now that oil is just floating there, making everything extra slippery. And we're just going to drive like normal. It's actually worse because it's going to be a combination of people driving like normal, which is too reckless, and driving too cautiously because they know it's more dangerous. So it's the delta that kills us. You know what I mean? If everybody is driving equally recklessly, then it kind of balances out, right? If everybody is up on 280 doing 90, then it doesn't even look like anybody's behaving badly, right? It's because everybody's speeding. You're like just driving along, it's like, oh man, we're all maniacs, apparently. The problem is when people are driving at a normal speed and you all come along at like 90. 90 is too fast, right? Normal speed, by the way, should be like 80 if you have a modern car. Modern cars can handle 80. 55 is for cars from like the 50s that were actively trying to kill you. That's why we have these stupidly slow speed limits. Like even 65 is just, it feels ridiculous. Don't you feel like you're going super slow when you're doing 65? Like on an open road. Your car feels ridiculous. If you're driving a car from the 21st century and you're doing 65 on an open road, your car's going, dude, what the hell? I can do more. Go a little bit faster. No. I don't want to get a trigger. You know what I mean? 80 miles per hour. I think that would be where most of the population is actually pretty comfortable driving. So that's where we should all just drive that. You know what I mean? Don't go out and do that. You'll get a ticket if it's your turn. I realize that it's just kind of randomly applied, but we just have to make sacrifices. It's like this weird ritual, right? Like I've been out on 280 driving 80 miles per hour and just been like passed by the police. The highway patrol, I'm like, oh man, I'm going 80 miles per hour. And like out of nowhere, highway patrol is like, wow, the lights aren't on. They're just driving fast. Wow, I could have gotten, what's he going to do? Pull all of us over? We're all doing it. So we all have to look around. You know what I mean? My favorite is when there's someone already pulled over and everybody slows down for it. It's like, well, what do you think he's going to do? He's already got one. You know what I mean? It's like the rest of the antelope can relax because the lion is already eating. What's he going to do? He's like, oh, so, well, I got this person. I'm going to write them a ticket for speeding. Whoa, look at all these people going. I'm going to jump in their car and get that one. They're not like cats where you can distract them with a laser pointer or something like that. To me, when he's already got one, that's the time we should all speed up. We should all just like haul ass by him and say, well, he's not going to get us. Go, go, go. Like, oh. And then the person driving the red car is like, oh, no, they're going to remember me. You know what I'm talking about? So, only if you're driving like a subtle car under the radar. Then you give him time to write the ticket, get back in his car. Anyway, that's beside the point. What are we talking about? Complex. So there's apparently a direct line from complex numbers to speeding, and I just don't know what it is. It seems discontinuous to me. All right, so let's talk about how complex numbers are going to show up with trigonometry. We've got to solve a couple more equations to deal with this. Now, this seems like we're doing a lot of background but that's only because we're doing a lot of background. We talked about complex numbers and when they show up. The solving equation thing is going to show up again. But before we get into that, we have to talk about powers of I. We know that I is the square root of -1. We also know that I squared is equal to -1. The cool thing about the imaginary unit I is that we only actually need 4 powers of it. After that, they just kind of go back to the beginning. Let's show you what I'm talking about. So I squared is -1. If I look at I cubed, if we think about I cubed, that's going to be I squared times I. That's just what exponents mean, right? I cubed means 2 i's, then 1 more I, but I squared is -1. So I cubed is -1 times I. Remember, the goal is that we only need 4 powers of I, because then they're all the same. So if I go up to I to the 4th, let's write down what that means. I to the 4th is I squared times another I squared. That's what exponents mean. Something to the 4th is just the squared one twice. But I squared is -1. And -1 times -1 is +1. If we go up again, if we look at I to the 5th, I to the 5th is just I to the 4th times I. But we just found out I to the 4th is just 1. Every time we get 4 i's, we can get rid of it. It's just 1, and multiplying by 1 doesn't do anything. And now we can see that we're in a loop. Because if I go up to I to the 6th, that's an I to the 4th times an I squared. I to the 4th is 1, and I squared is -1. So we just get -1. So now we're just in this loop. I to the 1st is just I. I squared is -1. Those two are just the definition of what we mean by this imaginary unit. I cubed is -1. I to the 4th is 1. I to the 5th sends us back to I to the 1st. I to the 6th is -1, because those 4 don't matter, and I squared is -1. So this is I to the 6th. I to the 7th is just going to be an I to the 4th times an I to the 3rd, and an I to the 3rd is -1. So I to the 7th. I to the 8th is just 2 i's to the 4, I to the 4ths. And I to the 4th is 1. Now we're just in this loop. We only need these 4 powers of I. I, -1, -I, I, -1, -I, 1. So this is also good. 1 is going to be I to the 8th, and also I to the 12th, and also I to the 16th, and so on. I to the 3rd, or -1, is going to be I to the 7th, and also I to the 11, and also I to the 15, and so on. -1, or I squared, is I to the 6th, and also I to the 10th, and also I to the 14th, and so on. I by itself is I to the 1st, I to the 5th, I to the 4 more is 9, I to the 4 more than that is 13. I spelled equals wrong. We only need these 4 powers of I. Every time we have more than 4, they pull out in groups of 4 as 1. So we just take the exponent and divide by 4 and look at the remainder, and that's the power of I that we use. Is everybody okay? Weird, this number I. Once we have these powers of I, we look at complex numbers, and we could think of complex numbers as just like polynomials. We're going to treat complex numbers like polynomials with this extra powers of I business. So for example, if I wanted to find the square of 3 plus 4i, I'm going to treat it like a polynomial, but instead of x, we're writing I. So we get 3 plus 4i times another 3 plus 4i. So it's going to be 6. Sorry, 3 times 3 is not 6. 3 times 3 is 10. Wait, no, 9. 3 plus 12i plus another 12i plus 16i squared. Or we might just remember how to square a polynomial and go directly to 9 plus 24i plus 16i squared. So start off, treat it like a polynomial, either by FOILing or just remembering how to square a binomial. Treat it like a polynomial, and then do this business with the powers of I. Replace your I squared with -1. And that was all in purple. So we have 9 plus 24i plus 16 times -1. So the 16i squared is just -16. And 9 minus 16 is 7? -7. How's that, okay? Seems like a lot to remember, but that's only because it's a lot to remember. You have to remember all of it all the time in person. It's also weird because you were raised to think of the square root of a negative number as being not a real number. And then we have the unfortunately named imaginary numbers. The next stage is that we've got to think about how we're going to use this information. We've got to try to put all this stuff together. But right now we've got 1, 2, let's see, 3, and then 4. You've got a lot of bullet points going on here. So let's say up next, So square roots and stuff we got a hold of, right? If I have the square root of 4, that's going to be 2 and -2. Oh, I shouldn't ask it as the square root of 4. I should say if x squared is equal to 4, then I get 2 and -2. Because when I write the radical, the square root of 4, we are talking about the positive one. So when we write the radical, we're specifically talking about the positive one. So we want to modify our language a little bit. When I write radical 4, when I say what's the square root of 4 and write it this way, I want to know 2. So I don't want to say it that way. But now I'm asking a different question. What are the square roots of 4? So 2 and -2. 4 has 2 square roots because 2 squared is 4 and -2 squared is 4. So if I have x squared equals -4, then we want to say 2i and -2i. Then we want to increase the degree . So the real ones we already know how to find. If x cubed is equal to 8, then we know 2. 2 is the cube root of 8. And that's the first thing we'll think of. What raised to the third power is equal to 8? 2. What raised to the third power is equal to -8? And we know we can get these real solutions right away. Up until this point in your mathematical career, those are the only ones we cared about. If I said solve the equation x cubed is equal to 8, you should say x equals 2 and then be done with it. But now that complex numbers have entered the chat, there are 2 other solutions. But those 2 other solutions are complex. This equation x cubed is equal to 2, or sorry, x cubed is equal to 8 has 3 solutions. We can tell that there are going to be 3 because it's an x to the third power. So it's got to have 3 solutions. We could also rephrase that question by saying that 8 has 3 cube roots. This is going to go further because then I'm going to write x to the 4th is equal to 16. And we're going to think of the 2 real solutions right away, but there are going to be 4 fourth roots of 16. There's also going to be 4 fourth roots of -16. The number of nth roots is always going to be n. So next time, we're going to figure out how to find these other complex roots. And we're also going to have to know how trigonometry enters into it. Any questions? That's a cliffhanger, but it's a math cliffhanger, so it's not quite as exciting as like a television cliffhanger. So next time, we'll find out. All right, that's it for today. That's it for this week. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.